This marks the beginning of a long journey for us. We have a year to spend together, right? You're going to follow the 8-topic, 8-day sequence, which ends up here in March 2009.
2 years, isn't it?
Huh?
Isn't it 2 years?
It's 1 year.
Oh, it's 1 year?
Yeah.
For 4 topics? And I'm teaching them?
Eight topics.
Okay.
So we have the program of that series on the handout for the second day, but it's also on the Mplus website, on the home page, middle column, bottom, where you will see then that what you learned today will be useful for longitudinal growth analysis that we're going to teach here in August. And what you will learn tomorrow will be very useful for what we will teach in the on the topic of mixture modeling, latent class and growth mixture modeling, which we will actually do a show on at the University of Michigan, Ann Arbor, in November. So you are smart to come in at the ground level, starting from the beginning. So this is, I don't know, third cycle? The cycles keep changing, so who knows?
Right.
But anyway, we have now renamed our day 1 through day 5 into topic 1 through topic 8. So actually, the first 2 topics, handouts, are on the website, I believe, as of today.
So we made a decision because the handouts that we were selling were getting so obsolete, because every time we teach, we create new handouts and we add new material. So we just, and the reason we sold the initial handouts was they weren't in a PDF. They were 1 million transparencies made in 1 million different pieces of software. But now we've converted everything. So we're going to be making every topic available in PDF form on the website at no cost. So you can, I mean, it was an administrative nightmare for us trying to sell these handouts. We had to get them Xeroxed, and we only charged the Xerox cost plus postage. But so anyway, we were really, it was torturous when Bengt converted everything to PowerPoint, but now that we've done it, we're just going to put them up there. And I think you'll find, those of you who have old handouts, that we keep adding, and they're getting closer and closer to being a book. They're getting more and more words and more transitions, and so I think you'll like them, even the ones you get today and the ones that you'll be getting, because the other topics we'll be putting up hopefully in the next few weeks, right?
Right.
Okay. And I have one administrative thing to say also, before Bengt gets started.
Take it away.
And that's that we found that it's best to hold questions till the end of each segment. So each segment's about 1.5 hours. So if you have a question, just jot it down. It's likely that your question will be answered in the next 2 or 3 slides. If it's not, then hold that question, and we promise we'll answer every single question, even if we have to answer questions during the entire break. So we'll never cheat you of getting your question answered. So that's the last administrative detail.
The idea is that just scribble down the slide number, and then we can just hit that right after.
Right.
With this new system, also, you will get the latest version of these handouts, because we keep, like Linda said, we keep adding pages, subtle changes, and make some little corrections. So in any case, we shouldn't hold up the exciting material that we have here. We're going to, for those of you who've been here before, you will actually discover that there's some novelties. We're going to sprinkle in some information about version 5, which has existed now since middle of November, but also sprinkle in some information about the upcoming version 5.1, which is taking shape right now and will be out sometime in April, if all goes well. And there are some exciting developments there that fits into today's topic. So without further ado, we'll talk more about general matters. For instance, well, I would like to say one thing. I'd like to welcome those of you who came from very far away, like Norway. Anybody here from Norway? All right. All right. Anybody here from Japan? I was curious. Australia? Mainland Europe? Okay. Anybody here who doesn't like to raise their hand? Thank you, Steve Martin. That's his joke. Anyway, all right. So here's the table of contents. So it's going to be a long day, folks, but a exciting day. And we just want to tell you, those of you new, why we made this software effort, because none of us had imagined doing so, although Linda has a background in software companies at the BMDP statistical software, where she was a customer support and a quality control person. So we felt that there's a very inefficient dissemination of statistical methods. I was struck by that because yesterday I was down in Washington, D.C. for the biometrics meeting, and many good methods contributions were presented. Really smart people talking about all kinds of methods. But they're not utilized in practice, and they are technically described in many different journals and very many different pieces of limited software that these statisticians write in programs like R that works for them but for nobody else. So we felt that we really need to have a program that integrates these methods, preferably in one framework. And our framework, our theme is latent variable modeling, and we'll see that that really is a general line of thought that covers a lot of very different techniques. We wanted the program to be easy to use and have a simple, non-technical language, which Linda created. So it is, as we say, nerd-free. That is, I was not involved. While still being extremely powerful. And we're happy to see that it's powerful to the point that actually these biostatisticians use it, which warms our heart. That is, it is quite unique in many features. So the first version came out, well, now it's getting close to 10 years, but we had 3 years development before then, right? So it's 15 years or something. And now we're November 2007, as I said, and then perhaps 5.2 here. It's almost like a version 6, it looks like now, but it will come out shortly. Team is small. Linda leads the effort, and I choose statistical directions. We have a great front-end programmer, Thuy Nguyen, and a genius statistical algorithmic programmer, T.M. Rasparojo, all of them telecommuting. Michelle Kohn runs the office and has now an assistant in Jean manning it. So that's the team. So it's a small one, but therefore a very nimble one that makes things move forward quite quickly. So let me do this. We are having this session recorded so that will hopefully be stored on the web in the future, and therefore serve as a background for those who couldn't come today but actually will come next time, and then they can study up on this. So we're going to try to be clear on what we're talking about here. We don't want to point on the screen because it ties us down to the computer, but I'll still try to make clear where we are. So we're going to talk about statistical concepts captured by latent variables for just a few minutes. And it's remarkable how many of them are covered by latent variable thinking. I was struck by that at the sessions yesterday at the biometrics meeting, ENAR. Latent variable modeling used to be a no-no among statisticians. They were quite skeptical about it. But now it's a mainstream statistical topic that was part of many sessions. And we like to make a distinction between continuous and categorical latent variables. Today we're going to talk about continuous latent variables only. And I think also in August, when we come back for the longitudinal topics 3 and 4, we're going to talk about continuous latent variables. Categorical latent variables won't come in until topics 5 and 6 in November, Ann Arbor. That's the mixture area, very exciting. but still we'll wait with that until we have more knowledge under our belt. And today then, continuous latent variables going to deal with measurement errors, factors, and not until August will we deal with random effects, frailties, liabilities. And the variance components means variation in hierarchical data, level 1, level 2, level 3, within between variation. And that won't come back as a topic until topic 7 and 8 in March 2009. So we're going to be in the left column, and the corresponding models that use latent variables in the left column are factor analysis models, structural equation models, growth curve models, and multi-level models. And we're only going to deal with the first two here. That's going to keep us busy today, and we certainly could spend perhaps yet another day on that topic here. But we're going to try to fit it into one day. So today's topic will be going from very introductory to intermediate to advanced. So I think even those who do structural equation modeling, for instance, on a daily basis, you're going to find that there are some things that you would like to hear more about and will hear more about here. So here is the general latent variable modeling framework. The boxes are observed variables, x and y, or u, as we call the variables that are not continuous, normally distributed or non-normally distributed, but they are categorical, dichotomous, ordinal, nominal, and count variables. And we're going to focus on continuous latent variables, so that will be f for factors. We're going to leave the categorical latent variable c for later on, for another day. And we're going to look at all of these possible relationships involving, in this case, today then and tomorrow, ellipse A involving the continuous latent variables. It moves. And when we get to August, we're going to talk about the separation between the modeling worlds of ellipse A and ellipse B, which have been separated before, but now are, as Timur likes to say, seamlessly integrated. And we hope you find them seamlessly integrated as well. So, and the last topic then is that we add one or more levels of data and do an analysis within and between clusters, so that you include multi-level modeling in this framework as well. And this is how excited we are about this. It hasn't blinked in years, has it? So anyway, by that we want to say that Mplus is actually several programs in one. Several programs in one, where you and what I'm going to say is it's not one program tacked onto another program. As many software packages are, you can do this, you can do that, etc. What we do is what it says on the last row, fully integrated in the general latent variable modeling framework. So it's fully integrated. You can do everything in combination with everything else, pretty much. So Mplus is a very good exploratory factor analysis program. You know, that kind of factor analysis that you get in SAS or SPSS, except Mplus is now by far the most comprehensive exploratory factor analysis program, and we'll tell you why in a little while. It is a structural equation modeling program, and we think it's by far the most comprehensive one in that set. We get a little bit miffed when people refer to Mplus as a structural equation modeling program, because then they ignore everything else below that the program can do, like item response theory analysis, which it does quite well. Certainly we can develop that area further, but it does some very unique things. For instance, item response mixture modeling with latent classes and multi-level item response theory. It does latent class analysis and latent transition analysis, also in the latent class mixture arena, very well. It does survival analysis, not only discrete time, but also continuous time survival using Cox regression, again, fully integrated in the general latent variable modeling framework. It does growth modeling, you know, the mixed linear model that you see in programs like SAS and other programs. It does multi-level analysis in general, you know, cross-sectional multi-level analysis like HLM and MLWin, and does some very unique things in that area as well. complex survey data analysis with sampling weights, clustering, and stratification is a particular topic that we have a grant to study. So there we feel we're at the cutting edge. And it's a program that can do Monte Carlo simulations quite easily, not only for methodological studies, but also for substantive studies where you want to figure out how believable your real data analysis results are. You can actually do a little so-called simulation to tell how trustworthy those results are. And we'll show you an example of that at the end of the day. So this then created, in the beginning of times, 5 days that we used to teach in one fell swoop in Alexandria, outside of DC. And remember those days, Linda? So we had it split up into cross-sectional longitudinal analysis, continuous variables, categorical variables, and we had day 1 corresponding pretty much to day 1 that we're doing today, topic number 1. But in other respects, this division into 5 days has fallen apart and grown. So we now have the 8 topics. Again, you find those on your second topics handout or on our website. So I won't go through that, but instead get going on regression analysis.
Thank you. Okay, just a couple of words before we start looking at this. And the one thing I wanted to say is that I don't want to stand in the lights. But anyway, Mplus is a program that's based on regression analysis. It estimates simultaneous regression equations. That's basically what it does. Today we're going to be looking at linear regression. Tomorrow we're going to look at regression for categorical variables, both binary and ordered categorical, nominal variables, count variables, all different kinds. So basically, it's just a simultaneous set of regression equations of different kinds. Regressions among observed variables of various kinds, among continuous latent variables and categorical latent variables. So it doesn't do anything magic. What it does is it takes a lot of different things and puts them together in a general framework where you can model your data and hopefully answer the research questions that you're interested in with the variety of possibilities that we offer. But today we're going to start and talk about linear regression. And I'm sure all of you have studied linear regression, but we're just going to refresh ourselves on a few points. Now, if you take a look at the scatter plot on the left screen, we have on the y-axis math 10 and on the x-axis math 7. And these are both continuous variables, so we're only in the realm today of continuous observed variables and continuous latent variables. And so when you want to regress math 10 on math 7, what you basically want to do is find a line that best fits that scatter of plots. And you want to minimize the distance between the observed data and that line. So that's the basic idea of fitting a linear regression. Now the regression model, actually I'm going to bring this over here. I'll just leave this on both screens for now. So the regression model we all know, y sub I is equal to alpha, which is some type of an intercept plus beta, a regression slope, times x sub I plus epsilon sub I, some type of a residual or error. The expectation or the mean of the error given x sub I is equal to 0. This implies that x and e are uncorrelated. The variance of the errors is a constant variance. So actually, I have to bring this other thing on. This is a long trek across the screen here. And what do we mean by a constant variance? So here we have math 10, math 7, let's say, and here's the regression line. And what we mean is that the errors here are normally distributed at each point on the line, they have a mean of 0, and they have the same distribution. So that's homoscedasticity, which I'm sure you're all familiar with. So we have the fact that X and E are uncorrelated and that we have a constant variance, or homoscedasticity. For ML, we also assume that there's a normal distribution. So this implies that the mean, the expectation of Y given X, and that's important, Y given X, not the mean of Y, but the expectation of Y given X is alpha plus beta X. This is referred to as the conditional expectation function. And the variance of Y given X is the variance of the epsilon. So these are, in the next couple of slides is basically a summary of all the facts of linear regression that you learned in probably a one-year course or something when you were in graduate school. So we have our population formulas, Y sub I equals alpha plus beta X sub I plus E sub I, or epsilon sub I, which we just saw. So now we're asking what is the mean of Y? So not the mean of Y given X, but the mean of Y. And it's the expectation, or the mean of alpha, plus the expectation of beta times X, plus the expectation of epsilon, which comes to alpha plus beta mean of X. So the mean of Y is equal to the intercept plus the regression slope times the mean of X. So we know that. And what's the variance of Y? It's the variance of alpha, which is a constant, so it doesn't have any variance, plus the variance of beta X plus the variance of epsilon. So this results in beta squared times the variance of X plus the variance of epsilon. Then we have the populations for the covariance, which is the mean of Y minus Y bar, or the mean of Y rather, times X minus the mean of X, which results in beta times the variance of X. So R squared is simply the full variance, which we just saw up here, beta squared times variance of X, so that's the denominator, and the explained part, beta squared times the variance of X. Standardized coefficients, the standardized regression slope is equal to the regression slope times the sample standard deviation of X divided by the sample standard deviation of Y. So these are the population, this is the population information that we need to know about the linear regression coefficient. And so let's talk about the parameters that we've seen in those equations. So which parameters do we estimate when we do the linear regression? The model has 3 parameters. It has alpha, the slope, alpha, the intercept, beta, the slope or regression coefficient, and the variance of epsilon. The parameters that are not in the model are the mean or the variance of the covariate, X. And that's important to remember, that these parameters are not estimated as part of the model. If you want to know what those values are, then just look at the sample statistics for the same sample that you're doing the regression on. But if you bring those parameters into the model, you're changing the regression model. Then you're no longer estimating the model conditional on X, but you're bringing X into the model and making distributional assumptions about it. So that's something that I don't think you always think about. You know, you might do your model command, and you just might mention the mean of X, or you might mention the variance of X or something, and then that just changes how Mplus perceives your model. So leave X as part of the model, but its mean variances and covariances with other X's are not part of the model. And here's our sample formulas. So the model estimated regression slope is equal to the covariance of Y and X over the variance of X. and the model estimated intercept is equal to the mean, sample mean of y minus the estimated beta times the mean of x, and the estimated variance of epsilon is equal to the variance of y minus beta squared times the variance of x. And our prediction equation, y predicted, is the model estimated alpha plus the model estimated beta times x. So this should, all be review. And let's take a look at an example where we have two covariates, x1, a dummy variable, for example, gender, and x2, a continuous variable. And that's something else to mention. The scale of the independent variables or the covariates is not an issue. So if you have a categorical, you don't have to declare independent variables or covariates to have a particular scale. In regression, they're either a dummy variable or they're a continuous variable. And in all cases, they're treated as though they're continuous variables. So when we study tomorrow, we'll be talking about different options in Mplus, like the categorical option, the count option, the censored option. Those apply only to dependent variables, not to independent variables. So here we've expanded our simple regression equation to include two x's. So we have y sub I with alpha, beta 1, x1, beta 2, x2, plus epsilon sub I. So the mean of y given x1 equals 0, x2, so x1 equals 0 means that term falls out, is alpha plus beta 2, x2. And the mean of y given x1 equals 1 is equal to alpha plus beta 1 plus beta 2 times x. And in the plot below, we've plotted the two lines. We have x2, the continuous covariate on the x-axis, y on the y-axis. The bottom line is for x1 equals 0, the top line for x1 equals 1. And the slope for x1 equals 1, or the intercept for x1 equals 1 is alpha, and for x1 equals 0 is alpha, and for x1 equals 1 is alpha plus beta 1. So with a dummy variable, when you go from one value, a dummy covariate, of the covariate to the other, it's just a shift. So it's a shift, and the difference between these two is beta 1. And as it says at the bottom, this probably looks very familiar to you because I'm sure you've all studied ANCOVA. So ANCOVA is an analysis of covariance where you have, for example, a treatment variable and then some type of a continuous control variable. And there are a lot of assumptions made in ANCOVA, these lines being parallel being one of them. This is also going to be coming back to us tomorrow when we look at differential item functioning. And this idea of the dummy variable being a simple shift from one value to the other with categorical or binary variables, we'll also see when we teach mixture modeling, when we have a categorical latent variable that predicts a continuous distal outcome, for example. That's just going to be a shift in the mean of that distal outcome by a constant. So we're going to go into an example now. So on the right screen, we have a path diagram. And in the path diagram, we have two covariates, male and math 7, and the dependent variable math 10. In the path diagrams that we're going to be seeing in the next 2 days, a square or a rectangle represents an observed variable, and an arrow goes from a covariate to a dependent variable. So this is the regression of math 10 on male and male and math 7. So we have two regression coefficients, beta 1 and beta 2, And we, of course, have our intercept, which doesn't show in the picture. Now, you'll note that we show a covariance between the covariates, but that's not part of the model estimated parameters. So we don't estimate that covariance. We show it in the picture so that you don't think that we fix it to 0. Sometimes people think because the model's estimated conditioned on X that somehow the covariances among the X's are fixed at 0, and this isn't the case. If you would just find those covariants by looking at the sample statistics, and the model is not estimated doing anything to those parameters. But we like to show it here so you don't think it's 0. So we, as I said, we have the intercept, the 2 slopes, and a residual variance, which is shown by that arrow. So an arrow going into a box or a rectangle represents the residual variance, or epsilon. And once again, reminding you that we don't estimate the means, variances, and covariance for the covariates. On the left screen, we have the Mplus Input. And I'll just take a minute for those of you who aren't familiar to just go over the Mplus language. We won't be focusing on that a lot during the course because it gets tedious, and I think there are more important things to talk about. But basically, the language is made up of a set of commands like title, data, variable, define. I think there's 9 now. And they're followed by a colon, and then each command, except title, just has the title. But the other commands have a set of options, and the options have settings that you can choose. So for example, the data command has the option file, and the file option is used to name this set of to give the name of the data set where the data is stored. It has a format option if you don't have free format data to give the format of your data, and many, many other options that you can read about in the user's guide. The variable command names the variables with the names option. It also gives information about missing data flags. So mother's education here has a missing data flag of 8. So for that variable, 8 is considered missing. We have a use variable command, which allows us to select a subset of variables from the names command that we're going to be using in the analysis. So here we say math 7, math 10, and male. In the define command, we can either create new variables or transform existing variables. And here we're saying male is gender minus 1, so that male is 1, and we'll be able to better interpret our data in that way. So then I'm going to skip the model command and just go down to the output command for now. In the output command, you can ask for additional output that we don't give by the default. So for example, Tech 1. Tech 1 gives you all the parameter matrices that are used to estimate the model. It shows you which parameters are free, and it shows you which starting values are used. SampStat, it gives you the sample statistics for the data that you're analyzing. It's always a good idea to have the SampStat option because it's a good way to catch if you're reading your data incorrectly. You're picking up the wrong variable or something. You just take a quick look at it and see if it looks right. And standardized is a way of asking for standardized coefficients in addition to the raw coefficients you get as the default. And when you ask for standardized, you'll also get Rsquare. We have a plot command with the option type, where you can choose different types of plots. And that's also a good way of getting a feel for your data by looking at histograms and scatter plots. And with more advanced analyses, there's other plots available too. So the model command is sort of the heart of Mplus, and it has several options that we'll be seeing as the days go on. The on option is short for regressed on. So to specify the model on the right screen, in the model command on the left screen, we say math 10, the dependent variable, regressed on male and math 7. So that's all we do for that. Excuse me. Okay, so then here's what we get by the request for SampStat on the left screen. We get the means for the 3 variables, we get the covariances, and we get the correlations. And as I said, this is a good way to just check and see, you know, am I really reading my data correctly? Because that's a lot of times when you're changing from SPSS or SAS or something to an ASCII file. I know SPSS sometimes puts blanks in for missing, and that can really create havoc for people if they're trying to read the data-free format. And just another thing to mention that I see on support, now we have large variances for Math 7 and Math 10. And this doesn't create any problems for us in our model estimation. But one thing to look at if you're having convergence problems is that sometimes large variances like this can cause a problem. So if you see in your sample statistics that you have a couple of really large variances and the rest are really small and you're having a problem, you should use the define command to just divide the variable by a constant. That does not change anything about the relationship of that variable to other variables if you just divide by a constant to bring that variance down to be more in line with the variances of the other variables. Okay, now we have this is old output. This is not version 5 output. So we haven't had time to change all of that yet. But let's talk about what's on this screen and orient ourselves a little bit. So the columns are the parameter estimates are in the first column here. The standard error of the parameter estimate is in the next column. Then we have the ratio of column 1 divided by column 2, which is a z-score. And that's what you can use to determine whether this parameter is significantly different from 0. Now, in version 5, there's a 4th column, and that 4th column is the p-value associated with the z-test here. And in version 5, the standardized information that's given in the last 2 columns here is given separately. So STD is a standardized coefficient, which is standardized using the variances of the latent variables in the model. Well, we don't have any latent variables in our model. So 0.763 is the same as STD. STDYX standardizes using the standard deviations of all of the observed variables, X and Y in the model. Now, we've also added a new standardization, and that's STDY. That standardizes just using Y standard deviation and is appropriate for a binary covariate, where we don't really want to standardize also with respect to X. So in this situation, male being binary, we would want the information for STDY. And in version 5 also, in addition to giving the standardized estimates, the 3 different kinds now instead of 2, we also give standard errors for them. And the output for each type of standardization will look exactly like the model results for the raw coefficient. You'll have 4 columns: estimate, standard error, estimate divided by standard error, and p-value. Now, if you ask for standardized, you're going to get all 3 of them. But you can also request just 1 of them or 2 of them. And those options are described in the output command. And on the very left here, the way that we present the results is we present it in the language that you state in the model command. So Math 10 on male, Math 10 on Math 7. Here's the intercept, alpha, and here's epsilon, our residual variance, Math 10, here. And then we had asked for standardized, so we get an R-square down here. Math 10 has an R-square of 0.622. Now let's take a minute to talk about the regression coefficients. So they're both significant, as we can see by the 3rd column being greater than 1.96. So it says that males have, in relation to females, have a higher mean on Math 10, and that as Math 7 increases by 1 unit, Math 10 increases by 1.059 units. So this is linear regression. Everything we're going to be looking at today is linear regression, something we all understand. For a 1-unit change in x, y changes the amount of the regression coefficient. So this is just a little summary and to sort of demystify what we're going to be doing. Everything is based on linear regression. So no secrets. Now, if you're not familiar, here's a few readings that you might consider looking at, or even just to refresh yourself a little bit if you feel like it. So now the next step is path analysis. So now we're going from one regression to more than one regression. So basically what path analysis is it's usually used to refer to regressions of observed variables. So once you go from 1 to 2, you're in path analysis, and you can have 10 regression equations, or 20 if you want to. You can have as many as you need to specify the model that you want to specify. And the important thing is that they're estimated simultaneously, so that you get the same correct standard errors. And this allows you to test direct and indirect effects. It allows you to test missing paths. If you put every path in the correlation matrix into your path analysis model, then it would be just identified, and there would be nothing to test. It would fit perfectly because you didn't leave anything out. But path analysis is a way to allow you to leave out information that you don't believe is important, and a path that you don't believe exists in your theory, and then test whether or not you can recapture the data using that particular model. So that's the second bullet: estimate and test theories about the absence of relationships. Okay, so the path analysis model we're going to look at is on the right screen. And the data, this is from Maternal Health Project MHP data. And there were a sample of mothers who drank at least 3 drinks a week during their first trimester, plus a random sample of mothers who used alcohol less often. The mothers were measured at the 4th, 7th months of pregnancy, delivery, and 8, 18, and 36 months postpartum. The offspring were measured at birth, 8, 18, and 36 months of age. There's a variety of variables here, but what we're looking at is mothers' alcohol and cigarette use in the 3rd trimester, and the child's gender and ethnicity as control variables. And the dependent variable that we're interested in is head circumference at birth and at 36 months. So there's 2 theories, and that's that the mother's alcohol and cigarette use affects head circumference, but once the child is born, that effect is no longer there. So it doesn't affect it anymore. The other theory is that even the effect that is found on head circumference at birth subsequently affects head circumference, so that effect continues. So what we're doing in the slide over here, we have mother's alcohol use and cigarette use in the 3rd trimester, the baby's gender and ethnicity, and as I said, we're including those as control variables because we know, depending on the gender of the baby or the ethnicity, head circumference could be larger. So we want to have those as control variables. Then we have head circumference at birth and head circumference at 36 months. So the paths that we're leaving out is the direct path from alcohol use to head circumference at 36 months and cigarette use to alcohol, or to head circumference at 36 months. So we're testing the theory that says once the baby leaves the womb, those adverse effects of the mother's drinking and smoking on head circumference aren't there anymore. Then the baby grows at a natural rate that is not depressed. So this is the Mplus Input to test this model, to estimate this model. There's nothing really new here, except we also have an option in the variable command to select observations from the data set. So use observations equals, and then you can set up some sort of a conditional statement and just take a subset of your data. The define command, once again, very useful. Here we are creating the mother's alcohol use variable. We're taking the log of it because it did not have a linear relationship with head circumference. At a certain point, the negative effect didn't actually go away, but the relationship got less. The slope got lower on that line. So once again, it's very simple to specify the model. We just use two on statements now because we have two regressions, head circumference on, 36 on head circumference at birth, gender and ethnicity, and then head circumference at birth on mother's alcohol use, mother's cigarette use, and gender and ethnicity. So we just specify that. And now we're going to be looking at some of the output from Mplus. So in a model like this, we have several tests of model fit. We have chi-square, and the null hypothesis is our model. So this is the H0 model. The H1 model is a model that has all of these variables freely correlated. So we want a large p-value because we do not want to reject the H0 model. We do not want to reject our model. So we have a large p-value here. So that means that this model, with the paths left out, does fit the data well. The RMSEA also indicates good model fit. And then here are our results. So the results, head circumference 36 on head circumference at birth, gender and ethnicity, and head circumference at birth on mother's alcohol use, cigarette use, gender and ethnicity. These are our control variables. And the important part of the model is right here, where we have our second regression, head circumference 0 on. And it shows that there is a significant, we look in the third column for significance, a significant negative effect of both mother's alcohol use and mother's cigarette use on head circumference at birth. And the left out paths don't make the model fit poorly, so we can conclude that we don't need those direct paths, so that there is no effect after birth of the use of alcohol and cigarettes. Now, once again, this is all examples that we give in the class use real data, but all examples that we give in the class aren't necessarily publishable. So, this is an illustration only. So we always have to say that just to make sure. As for the rest of the output, we have a residual variance for each of our regressions, and we have our intercepts, and we have our R-square. And that brings up another point. Notice how small the R-square is for head circumference at birth, 0.08. And this is something else that comes up often on support and Mplus discussion that probably can be repeated here, and that's that a well-fitting model, well, first of all, R-square is not a test of model fit. R-square tells you how much variance is explained in each regression. So you can have a very well-fitting model that has very small R-squares, or you can have a very poor-fitting model that has very large R-squares. So not to look at R-square for model fit, but to look at R-square to tell you, gosh, there must be something else going on besides mother's alcohol and cigarette use that has something to do with the head circumference at birth. So now we have a way of testing these indirect effects. So when mother's alcohol use goes through head circumference at birth to head circumference at 36 months. That's called an indirect effect. Gender to head circumference at 36 months, that's a direct effect. Now, you know, we have regression coefficients for each part of this indirect effect, and we know whether each one of them is significant. But what we want to know is the entire indirect effect significant? And the indirect effect itself, the parameter estimate, can be estimated or can be calculated by multiplying the regression coefficient for head circumference at birth on mother's alcohol use by head circumference at 36 months on head circumference at birth. So the product is the indirect effect, but you need a standard error to know whether that indirect effect is significant. So that's why we created the model indirect command. So you can request indirect effects and their standard errors. The default is delta method standard errors. We also have a bootstrap option in the analysis command, and you can use that to get bootstrap standard errors. And if you ask for the standardized option in the output command, you're going to also get standardized indirect effects. So model indirect is quite useful. We also have an option called C-interval in the output command where you can ask for confidence intervals. A lot of times people prefer to look at confidence intervals than statistical tests. And we have three types. Symmetric, which is just the regular, the parameter estimate plus or minus 1.96 type thing. But we also have bootstrapped and bias-corrected bootstrap confidence intervals. And these are based on the bootstrap distribution of each parameter. They take non-normality into account, and they may, because of that, not be symmetric around the parameter. So these are options that you might be interested in that we're just mentioning, not really going into too much. We are going to look at, let me just see one thing. What's next? Okay, then I'll just stay over here. So here's an example. It's actually from the user's guide. So here's a model, a path model, where we have two x's observed, x1 and x2. We have y1 and y2, which are mediator variables, and then a distal variable, y3. And in model indirect, we have two options. Ind, where you can just request a specific indirect effect, or a set. So you could say that you just want y3 ind y1 x1. So that's going to be x1 to y1 to y3. You could just ask for just that one. Or you could say y3 ind x1, and then you're going to get every way to go from x1 to y3. So you can go from x1 to y1 to y3, x1 to y2 to y3. Is there another one? Oh yeah, x1 to y1 to y2 to y3. So it'll give you every one. It'll figure them out and give them all to you. And the via option is used to request a set of indirect effects that includes specific mediators. So y3 via y2 and x1, we always want the mediator of y2. So model indirect is available, and you can use that for indirect effects for both continuous and categorical variables at this point. And for further readings on this topic, we have these articles by Dave McKinnon and Pat Shroud. And this is the article, I think, that we use primarily for the work that we've done in Mplus, based on his information. Yes, and I think it's your turn. We should probably stop at 5 after 10.
Okay.
Or to be done. Do you agree?
That's good. Okay, that's great. And now we can add that David McKinnon has managed to finish his book on mediational analysis, which is available and recommended as a good summary of the field. I just wanted to go back to one slide. I thought it was very good, useful that Linda went through these formulas. Although they look boring, they actually carry a lot of information that is practically useful. One formula that keeps tripping people up is that, I'm looking at slide 18 here briefly again, equation 2. One formula rather, that keeps presenting a problem for people. They forget that the mean of y is equal to the intercept plus the slope times the mean of x. This happens in many situations. We're going to see it this afternoon, where this simple formula is embedded in a multiple group analysis, where you may hold the intercepts equal across the groups, but given that the second term is not equal across groups, the means of y will not be equal. So sometimes people think that alpha here is the mean of y, but the difference is this extra term beta times e of x. And that comes into play also in growth modeling that we're going to talk about in August, when you come back in August. Namely where the dependent variable could be a random intercept or a growth factor. Could be a growth factor, and you're interested in the growth factor mean, but you don't estimate the growth factor mean, you estimate alpha and beta. And x will be, say, a time invariant covariate, and people get upset when they see, say, a negative alpha when they know that their observed mean or dependent variable growth factor mean is positive. Of course, this could be positive, e of y could be positive, and alpha could be negative, because this second term beta times e of x is positive. So, seemingly simple little facts creep into these more complicated models. So it's good to have them straight from the beginning. Now let's go to slide 30, or slide 40, rather. And now we get into the core part of today. I'll stand over here just to balance Linda standing over there. So we're going to talk about measurement error, which then leads to factor analysis and structural equation modeling. Measurement error is something that creeps into most of our measurements, I would say. And it can then cause problems like attenuation of the correlations between the observed variables. They turn out to look smaller than they actually are if we could have measured the phenomenon without error. And we can make a distinction between measurement error in the independent variables, the variables that we call x variables so far, and measurement error in the dependent variables. The error is particularly serious if it happens in the independent variables, because then you typically get attenuation in the regression slopes. So a regression slope that should be representing that steep of a line turns out to be giving a much flatter line, a weaker relationship between y and x. And we can take a look at how that comes about. A measurement error in the dependent variable doesn't create a bias. And I should mention, actually, that's not always an attenuation. It could be an overestimation if you have more than one x variable and only one of them has a measurement error. But typically, it's an attenuation. In the dependent variables, though, it causes an increase in the standard errors, because you have an increased variation due to that measurement error. And the standard error is going to be bigger for your slope, for instance. So your confidence interval is going to be bigger. You're going to have a less precise statement of the strength of relationship between your y and x. So we're going to try to take measurement error into account. That is, we're going to accept that they are there, and we're going to try to build models that accommodate these errors so that the model parameter estimates are going to be purged of negative influence of the measurement errors. Of course, that then assumes that we do the modeling right, and that's what this whole day is about, to try to do modeling that's realistic. And that's not an easy task. So, two ways to deal with measurement error that's occurred in the psychometric literature. There are many more in the statistical literature, I should say. Single indicator of a latent variable. Sometimes people like to plug in a known measurement error. For instance, you have a measurement instrument that's been existing for many years, and you even have manuals which says how reliable that measure, that score is. Well, if you know that from previous samples, pilot studies, then you can plug that into the model and get a disattenuated regression slope that way. And we'll show you how to do that. Not necessarily the best way of approaching things, because the reliability estimates may not be relevant for the situation that you're looking at. So instead, we're going to focus on multiple indicator situations. We try to measure the latent variable, the factor, by several different indicators, capturing different aspects of the factor, which then allows you to actually model this measurement error and estimate the measurement error, and more importantly, estimate the real relationship, what we call the structural relationship, without influence of error. So if you look at slide 41, we have a set of formulas here. They're very simple, again, building on regression. And we're going to talk about a factor or latent continuous variable now as eta. So this is eta, the Greek eta. And we're saying that what we're really interested in, we're going to focus on the measurement error on the x side now. We're interested in regressing y on eta. Here's the equation for person I. So we're interested in beta. And we're going to call beta a structural slope. It becomes structural because we have a latent variable there. Later on, we're going to think about it as a factor loading. Factor loadings are slopes. But let's think about it as a fundamental regression slope that we're interested in. Now, the problem is we don't observe eta. We only observe x. And x is a measure of eta, some latent variable construct, measured with error. So x is equal to eta plus an error, delta here. We're going to use a lot of Greek. It's good for you. So we have a residual here, delta, which makes x different from eta. And we're going to talk about these residuals. We're going to be forced to assume that these residuals are fairly, although they acknowledge measurement error, they're fairly well-behaved residuals. Well-behaved in the sense of residuals in linear regression. Namely, they are, as Linda pointed out, they are uncorrelated with the right-hand side variable. So the bigger your factor value is, you're not allowed then to have a bigger measurement error. The measurement error should not be correlated with eta. And homoscedasticity as well. So there are assumptions, but let's say that this is a well-behaved error. Then the variance of x is the variance of the factor plus the variance of the residual, and therefore we can talk about the reliability of x. The reliability of x in its measurement of eta, and we have a reliability formula, and if you look at it, you see it's exactly what Linda described as R-square. Namely, in the denominator, the downstairs expression, you have the total variance of x, and in the upstairs, in the numerator, you have the explained part of the variance explained by the factor itself. So reliability and R-square is one and the same thing. So we're going to try to connect terms here now as we go along. And we're going to see then that the higher the reliability of x, the better can we capture the true beta. So let's look at that. So if now up here we regressed on true eta, now we're regressing on x, which is all we have observed-wise. So we have y equals now alpha star and beta star. They're no longer the same regression coefficients because we're regressing on x instead of eta. And then beta star here is the usual formula then for beta, as Linda pointed out. If you look at her formulas back there on page slide 17 or 18, beta is the covariance between y and x divided by the variance of x. That's a standard formula for a single x. Well, it turns out that the covariance between y and x under this model with measurement error, covariance is the same as between y and eta, so the covariance is not affected by measurement error. Only the correlation is. The covariances are not. And in the downstairs expression, variance of x, well, we agree that that's the variance of the true factor plus the variance of the residual. So that ratio is not beta, but it's less than beta. It would have been beta if we didn't have the bottom right-hand term. If we didn't have variance of delta, then we would have covariance between y and eta divided by variance of eta. That's the regression formula, right, for getting beta out of this top equation. But we have this residual variance extra, so a bigger denominator, which makes this less than beta. So we're saying that when we regress y on x, and we're estimating beta star is going to be too small relative to the true beta, so we have an attenuated slope. And it's attenuated as a function of the reliability. So on the next slide, you have an example. Slide 42. Say that the true slope is 0.8 in the regression of y on eta, and say that the residual variance is 0.43, whereas the true variance for eta is 1, which says that the reliability for x is 0.7. Well, if you do then the regression of y on x, you're going to estimate beta star, which is not beta. It turns out to be 0.56. So 0.56 being considerably less than 0.8 for a realistic size reliability of x of 0.7. So here you see the attenuation. It's plotted here. Here's the true line that we're after with slope beta, but we don't observe eta. We work with x, and we therefore get beta star and a flatter, more attenuated line. So that's pretty straightforward and clear. Now, slide 43 then says, well, what do you do about this problem? Well, like we said, one approach is to say that we know the reliability or the unreliability. We know the measurement error, or we know the measurement error variance, rather. And so let's say then we have only one indicator, x, one measure of eta, in which case we are going to now start bringing in factor loading matters. We're going to have a lambda here, a slope of x on eta, but for simplicity with only one indicator, we can fix that to 1. So that doesn't play into the picture. Variance of y is going to be equal to psi, psi being the upside down pitchfork. It's the variance of the factor plus theta, which is the variance of epsilon. And this is a notation that we're going to use throughout the 8 days we might spend together. Psi, variance of the factor, theta, theta, variance of epsilon. So this says that the reliability then is the explained variance, psi, divided by the total variance, which is psi plus theta. Now, in these models, the variance of y can be estimated as a sample variance, which means that if you look at this formula, you have reliability equals psi times variance of y, which means that reliability times sample variance, which is the estimate of this, moving that up to the left-hand side, is equal to psi. And if you look at these statements long enough, they will confess to you then that theta equals 1 minus reliability times sample variance. So what does that mean to you? Okay. Theta was the residual variance. So what you say, you observe the sample variance of y, sample variance of x in this case. It should say variance of x here. So that's one thing we should mark. Variance of x, not variance of y. So sample variance multiplied by 1 minus reliability. Reliability is what you get out of your manual for your measurement instrument. And then you can create this value, which is the residual variance, which is your estimate of the residual variance. So that is known. And then in Mplus, we'll talk about factor analysis and the by statement, but we just want to have this here for completeness. We're going to put in to the residual variance here. You may want to circle this line here, y at a. Y at a is the residual variance for this indicator of the factor, and that residual variance is the theta value that we computed. So by these two lines, factor loading fixed at 1 on the first line, and a residual variance fixed at the residual variance value that you get out of reliability on the second line, you have in effect taken into account measurement error with a single indicator. So that can be done. It's a standard SCM, structural equation modeling trick. And again, it should be used with caution. We've seen examples where people use it for every single variable in the model, and we wonder where they get their values from. I'm sorry, what?
You mentioned that should be a variance of x.
Yes, so all of these y's should be x, yes. All of the y's should be x. Sorry about that. Then let's focus on slide 44, which is the real situation we're focusing on here. Now we're going to talk about having at least 2 and preferably many more indicators of a factor. So you have the same factor up here in the equation on the right-hand side, but you have 2 different measures, x1 and x2. And now we're going to get back to linear regression once again. We're going to have an intercept, although we're going to use funny words. We're going to use another Greek term, nu, N-U, nu sub 1 is the intercept in that equation, and lambda 1 is the regression slope. And the residual, which we call delta 1, is the usual residual in the regression. And for variable 2, we have just subscript 2 on those. So it's 2 regression equations. The only new thing here is that eta is unobserved, a latent variable. And we're going to focus on how we can work with latent variables in linear regressions. So you can show this as in the diagram with x, be it x1 or x2 on the y-axis, and eta on the x-axis. Now you have the 2 lines here. And what's the meaning of this? Well, you try to measure, say, math ability on the x-axis here. As eta increases, your math skills increase. But you have 2 different tests, x1 and x2. Say x1 may be a word problem, and x2 a problem that is not word or reading ability related at all. Then as your ability increases, the expected scores on these 2 variables may increase at different rates. So this particular test, x1, is more sensitive to a change in your math ability. It increases more rapidly than the second test. So in this case, you may want to write this, lambda 1 is greater than lambda 2. And also at the low values of eta 0 here, the intercepts may be different. So they're on different scales. They react differently to your math ability variation. So that's a natural parameterization to allow for both the intercepts and slopes that vary across the indicators. Now we're getting into some interesting action here, which sets the stage for exploratory factor analysis. Let me put this somewhere here. So slides 45 and 46, I think, are key slides for understanding the pitfalls of trying to do latent variable modeling. What we look at on slide 45, at the top there, is a model diagram representing actually your first structural equation model. Already before the 10 o'clock coffee break, you get your first structural equation model, because we want to point you in the right direction. So what is it? Well, you have a y variable as a dependent variable, and it's regressed on a latent variable, which is then in the circle, latent variable eta. That's the regression that we looked at before, y regressed on eta, and we're very interested in that slope beta. But we can't really measure eta perfectly. For instance, Linda talked about alcohol consumption during pregnancy, where the mother may not give reliable measures, reliable responses to the question. You could, in fact, use, these mothers were asked several times during their pregnancy what their drinking frequency was. So you could have 2 time points, X1 and X2, being different reports. Or as in the dietary fat intake literature, they often use a survey questionnaire question, X1, and at least for a random subsample, a more detailed dietary diary, try to say that fast, which would be X2. So 2 different ways of getting at the true value. The true value influences the responses. The arrows go out from eta. But the x's are not the same as eta. They have residuals epsilon 1 and epsilon 2. But all of these paths represent linear regression. Y on eta is linear regression with residual sitting here. They call it Z or Z, in line with the standard SEM literature. And the regression of x1 on eta is linear with residual epsilon 1. The regression of x2 on eta is linear with residual epsilon 2. Blood pressure is another example. Blood pressure is not without measurement error, not so much in the measuring device, but you may have, across time, irrelevant variation. Your measure in the morning may be different than in the afternoon. You're really interested in some kind of stable level of measurement or blood pressure, which is eta, and x1 could be the morning measure and x2 the afternoon measure. So we have measurement error all over the place. Beta, as it says in slide 45, gives the correct picture, free of measurement error, and also has the advantage of avoiding collinearity that you would see if you regressed y on x1 and y on x2. Collinearity being that you have 2 x variables that are highly correlated, and we know from linear regression that that can cause problems. So anyway, the equation here at the bottom of 45 is the way to get beta. And in the afternoon, we'll actually talk about how one can deduce that that's the right formula for beta when we talk about identification matters in structural equation modeling. So I won't take time to talk about that now. But what I want to focus on and stress here to motivate our expansive description of factor analysis of both the EFA and CFA kind is that any measurement modeling is fraught with dangers if you don't do it well or carefully. Take as an example the situation where the 2 measurement errors are correlated. You have a double-headed arrow between epsilon 1 and epsilon 2, which means that you have a theta sub 21. You have an off-diagonal element in theta, so to speak. You have an error correlation here. Take, for instance, the dietary fat intake example. The survey measurement response that you give may over or underestimate your dietary fat intake, as may your diary. You may have a systematic error in your reporting. And so that if epsilon is, measurement error is high for one measure, it may be high for the other. Well, it seems innocuous that you have a little measurement error correlation here for the 2 indicators, the 2 measures of your true dietary fat intake. But in these models, particularly in some situations, these models are quite sensitive in the sense that this, leaving out this little error correlation will harm the estimation of what you're truly interested in, namely beta. So a misspecification out here, seemingly innocuous, has severe consequences for the structural parameter beta that you're interested in. And that's a situation you want to protect yourself against. So you have a hypothetical example here, beta 0.5, the true value is 0.5, and that's in both, there are 2 different examples in the 2 columns here. Beta is 0.5 in both cases, but the reliability of X is different. reliability of x of each of the two x variables is 0.5 on the left and 0.8 on the right. And if you plug in values, reasonable values, I won't take time to go through them here, reasonable values for the parameters of the model, the estimate of beta here is going to be, with reliability at 0.8, it's going to be pretty close to the true value. It's going to be 0.48. It should be 0.5, but it is 0.48. But if the reliability is low, then your estimate of beta is going to be distorted to, actually this value is wrong. It should be, if you look at the formula bottom left here, in the denominator it should be 0.1 here. And at the bottom, instead of 0.36, it should be 0.41. But it's still a more pronounced misspecification, attenuation of beta with a low reliability for x. So that if you plug in this model and you get the regular maximum likelihood estimate out of any program, it will be incorrect when that measurement error is there and you have not accounted for it. You are less harmed by that if you have fairly low measurement error in the x's. That is, it has to do with the reliability of the x's, how much that misspecification is going to hurt you. So if you have very reliable measures, such a misspecification is not so serious as it would be if you have fairly unreliable measures. 0.5 is a fairly low reliability coefficient. Now you may say, well, why don't I just estimate that residual correlation? Shouldn't that be possible in SEM software? And yes, in principle, this can be estimated. And a theme that we're going to have is as long as you can estimate a parameter that has to do with measurement error, your results are going to be fine. But this is an example of a parameter that is not identified. There is not enough information in the data to estimate, to identify and estimate this parameter. It cannot be estimated. So even if you really suspected that you have a high correlation here between the residuals, you're not going to be able to estimate it. Or you may guess that is 0.2 and fix it at that and do a sensitivity analysis, but that's not very satisfactory. So this is an example then that says you shouldn't work with only two indicators. You should not work with such few indicators. You should have a whole set of indicators, and you should do exploratory and confirmatory factor analyses so that you could detect which items may have correlated errors under the assumption that most items won't have them. This is probably a reasonable assumption. But in any case, never end up with only two indicators. We recommend at least 4 or 5 per factor, where you have the if you have that many, you have the possibility of having correlated residuals between two of them. So this is a complex picture here, but there are 2 take-home messages. 1 or 3. One, it isn't an innocent activity to do measurement modeling. You really have to think about what you assume. And uncorrelated residuals is a possibility. And the first point is then that if you ignore them, if you ignore that possibility, you may hurt parameters in the important structural part. It's not just an academic concern for the measurement part, but it influences the structural part. And the other point is that you really want to have more than 2 indicators per factor so that you can allow for some of the indicators having correlated errors, whereas others don't. And the third most important point is, how do you select the indicators? Well, you should start from a larger set and do exploratory and confirmatory factor analysis. And I think by that we should... It's up to you.
Okay, so let us take questions and we'll take a break then. Yes.
Just a quick question on that last point. Would you then go through a process selecting different sort of correlations between indicators and seeing which ones fit the data best? I mean, I've seen people argue for like consecutive questions on a survey instrument, so they'll correlate consecutive items, or maybe correlate the reverse coded items. Are there rules? I mean, it seems random how you correlate items and not others.
So for those of you who can't hear the question is about, are there any rules for how you would correlate errors to fit the data better?
I guess what I would do, first of all, I would have a lot more factor indicators, like 5. And I would probably, and we're going to be going through exploratory and confirmatory, but look at modification indices as a first step. But if the parameters aren't,
Well, I think you're right. You should
Yeah.
you would start with the exploratory factor analysis first.
right.
And we're going to show you today a new way of doing exploratory factor analysis where you can allow for correlated residuals if your theory postulates, measurement theory postulates that they should be there.
So
You know,
maybe
it's
we
some-
should come
some
back.
set-
Oh, go ahead.
Yeah, some sets of items have the same stem, so they could correlate for those reasons. So there are possibilities to build in the knowledge about your measurement instrument while still doing exploratory factor analysis.
So I think by the time we've gone through exploratory and confirmatory, you'll have more ideas. But as far as like rules, I don't know of any. I think most of the time when a person's doing, you know, an analysis, you have your theory that's guiding you, and you do what's logical. And hopefully it's supported, the reviewer agrees with your logic. Have a question over here?
Are there any well-known examples of often cited examples in any substantive domains that you know of where correlated errors have resulted in dramatically attenuated estimates of structural parameters?
So the question is, are there any published examples of this kind of a problem, correlated error causing harm on the structural parameters? I'm not aware of them.
I would imagine there's a lot of published results, though, that have that problem, but it's just not acknowledged because nobody really thought about it. But who studies measurement error like that might, who might be somebody that would have something like that would narrow his search?
Actually, I know of an example.
Oh, here we know somebody.
Okay, good.
There's an example in dietary research. There's the open study that measured true, from a biological marker, true energy and protein intake. And then it did a frequency questionnaire and a diary. And they found that there were definitely correlated errors.
Okay, so this person is giving an example from the dietary world, measuring dietary intake.
It's called the open study.
They call the open study, where there has been a work on estimating measurement error correlations of this kind. So maybe we can get that reference later on.
Could you email it to us? At either Bengt or me?
Yes.
On slide 24, when we're talking about dichotomous variable, you said that Linda, you said that you would use a different estimate. Would you report in a paper the estimate for male as being 0.028, or would you use the?
No, I would use the.
So just to repeat the question so we
question, I
get
keep
it
forgetting.
recorded as well. So the question is, for this slide 24, the regression of math 10 on male, we have 0.028 as the doubly standardized estimate. Would we report that?
I would report for all binary covariates the new STDY column that we give, and for all continuous covariates the STDYX. You can add to that if you
The
like.
idea being that for males, you're not interested in the standard deviation change of gender, but change from 0 to 1. So you would not report this one. You would report the value that we don't have here.
You report the value that you don't have.
Yeah. Well, we do have it
We
in
do
version
have it,
5.
but we don't have it here with us.
The way you can do it here.
So you wouldn't use the estimates that said 0.763, which some people might mistakenly do.
You can certainly use the raw estimate, and actually,
But if you wanted the standardized one,
if you wanted to standardize it, you would standardize it only with respect to math 10.
I mean,
Divide by the standard deviation of math 10 only.
maybe we should just say that we're not advocating necessarily using standardized estimates.
Okay.
We would use raw estimates. But if you're going to use standardized, for binary covariate, use STDY, and for continuous covariate, use STDYX. In fact, I would say we never use standardized. We should never say never, I guess.
There's a big debate about whether or not to use standardized estimates, and we can talk more about that later maybe, but I certainly, and you too, Linda, tend to go with a raw estimate to the extent that we can understand what the results are. Sometimes you want to have things on a comparable scale, and standardization is useful to some extent, but it has its pitfalls as well. Anyway, I think that's sufficient for now. Yes, in the back.
When I took a regression course, I seem to remember being told not to worry about measurement error in the predictors, more in your dependent variable. It seems like what you're saying here is that almost all regression models are producing biased parameter estimates, if this is the case. I can't quite, reconcile that. I was wondering.
Yeah, so the question has to do with measurement error. Which is worse, having measurement error in Y or in X? And it is a fact that it's measurement error in X that is harmful, that attenuates the slope, not measurement error in Y. Measurement error in Y is harmful only to the extent of increasing standard errors and the confidence intervals, whereas measurement error in X will attenuate or at least bias the slope.
Right, but I'm saying that most people use X without worrying about measurement error.
Oh, I see what you're saying. Most people use X without worrying about it, yes.
Right.
And therefore they have biased results if they have measurement error, yes.
So most regression models then are biased results.
Yeah, most regression models.
That's what I'm worried about.
I think that's why structural equation modeling was invented. Yeah.
And then it had its misuses.
Yeah, that's why structural equation modeling was invented, and as Linda adds, it comes with its own pitfalls, namely careless modeling, which we're trying to teach you to avoid during this day.
Very quickly, on slide number 35, the question I have is about the model indirect test, and wondering about Sobel's z-test and whether that links in here with the tests that are provided in Mplus.
So the question is about slide 35, model indirect, and Sobel's z-test. And Sobel is Michael Sobel at Columbia University, and I think he is the person who first described the delta method. So that is the delta method, yes. Yeah.
Exactly. Perfect.
That's good that we come together in terms of terms here. Yes, in the front.
Just a quick question. Those epsilons that you show, for example, in slide 45 and elsewhere, are they really deltas and not epsilons?
Oh, well, good. Okay, slide 45, those epsilons, I guess they could be deltas, yes. Right, thank you.
I saw earlier,
Yes.
you were talking about
Yes.
just in general measurement errors for the X
Right.
variables.
Right.
Delta was used, and then all of a sudden we moved to epsilon, so
Yeah.
it really is a delta. Okay, thank you.
Would you change that?
Yeah, that's, it is a clash between two cultures here. In the old literal world, deltas were measurement errors for x's, and epsilons were measurement error for y's. So I was stuck in that when we did that slide, but then in the Mplus program, we do what in literal will be called the all-y model, so all measurement errors are epsilons. So. Good, thanks for that catch. Yeah, epsilons and deltas are essentially the same things.
We have a question over here.
Is it the same case on slide 43 then?
I'll let you do that.
The top?
Yeah, epsilon and delta, it doesn't matter. Just think of it as a residual. So if you want to be consistent with Mplus, it should be epsilon everywhere. Yeah. Thanks for catching that.